Hello everyone, welcome to the Quantum Computing for Beginners series. I am Abhijit Chitrapu and together we are diving into a fascinating world of quantum computing. In this series, we'll unfold the complexities, demystifying the magic and make quantum computing accessible to everyone, especially those passionate about computer science. Our main goal is to break down the barriers surrounding quantum computing so that each of you, no matter your background, can gain a solid understanding of this revolutionary field. We are here to explore the details, potential applications, and the profound impact quantum computing is making on the landscape of computer science. Now, why should computer scientists care about quantum computing? Well, quantum computers have the potential to solve problems at speeds unimaginable to classical computers. They bring new dimensions to cryptography, transform machine learning, and open doors to uncharted areas in various computer science applications. Get ready for an exciting journey as we delve into the quantum computing together. Now let's address the big question. Why does quantum computing matter in the world of computer science? It's not just about solving problems at incredible speeds. It's a model shift. Quantum computing has the potential to reshape the entire landscape of computer security and more. Today, we'll explore the significance of quantum computing, laying the foundation for the transformative power it holds. We'll also outline what to expect in the upcoming episodes, from the fundamentals of the quantum mechanics to the details of quantum algorithms. Each episode is stepping stone in our quantum exploration. This revolutionary approach to the computation is unlike anything we have seen before, drawing its strength from the fascinating principles of quantum mechanics. At the core of quantum computing lies a fundamental departure from traditional computation. While classical computers use bits that can exist as either 0 or 1, quantum computing introduces a game changer, the quantum bit or qubit. Unlike its classical counterpart, a qubit can exist in multiple states simultaneously, thanks to a phenomenon known as superposition. You need to imagine this. Classical bits are like light switches, either one on or off, 0. But qubits, they are more like dimmer switches, existing in various states at the same time. This unique characteristic of superposition rapidly increases the computing capacity of quantum computers, allowing them to process vast amount of information in parallel. Why does quantum computing matter? It goes beyond just speed. It's a fundamental shift in how we approach problem solving. Consider this: problems that we are once taught to be unbeatable for classical computers can be tackled in a fraction of time by a quantum computer. Think of it like trying to find a traditional needle in a pile. Classical computers check each piece of straw one by one, while a quantum computer explores multiple possibilities simultaneously, making the impossible seem routine. This just not a theoretical one. Quantum computing has the potential to transform fields like cryptography, automation, and drug discovery, among the others. It opens doors to solve complex problems that were previously beyond our reach. Quantum mechanics, the physics of the very small, introduces us to concepts that defy classical institution. Today, we will unravel the fundamental pillars: qubits, superposition, and entanglement. In the quantum universe, information is stored in quantum bits or qubits. Unlike classical bits that can be either 0 or 1, qubit can exist in a state of superposition, representing both 0 and 1 simultaneously. You need to imagine this. Qubits hovering in a blurred state of both 0 and 1 at the same time. This unique property exponentially increases the computing capacity of quantum systems. Superposition is the enchanting dance of quantum states. It allows particles like our qubits to exist in multiple states at once. Imagine a spinning coin frozen in midair, representing the coexistence of 0 and 1. This fundamental principle forms the bedrock of quantum parallelism. Quantum entanglement introduces a profound level of link. When qubits become entangled, the state of one qubit becomes fundamentally linked with the state of another, even if they are light years apart. Changes to one qubit quickly affect its entangled partner, showing this mysterious phenomenon of quantum entanglement. Why does all this matter again? Understanding these quantum mechanics fundamentals unveils the immense potential of quantum computing. These principles enable quantum computers to process information in ways classical computers cannot, promising a revolution in computation and problem solving. Here, we unravel two captivating principles that take center stage: the mesmerizing wave particle duality and the interesting Heisenberg's uncertainty principle. We have the mysterious concept of wave particle duality at the quantum level. Particles defy our classical expectations, revealing an astonishing dual nature. Imagine a cosmic ballet where particles surf on waves of probability. This principle challenges our conventional notions and invites us into quantum dance of uncertainty. Something like electrons behaving not just as particles but also as waves, existing in multiple states simultaneously. It's a mind bending concept that challenges our perception of reality. You need to imagine a ballet of particles surfing on waves, expressing the essence of wave particle duality. Now let's dive into Heisenberg uncertainty principle. This principle introduces an element of unpredictability into the quantum tapestry. It asserts that the more precisely we measure a particle position, the less precisely we know its momentum, and vice versa. This inherent uncertainty speaks to the dynamic and elusive nature of particles at the quantum level, disrupting the deterministic worldview of classical physics. It's like trying to pin down a quantum butterfly. The more you focus on its position, the more its momentum slips away. Heisenberg's uncertainty principle adds a layer of unpredictability, challenging our ability to precisely measure both position and momentum simultaneously. Now, why does these principles matter to us? They're not just abstract concepts, they're the very essence of quantum mechanics. Where particle duality challenges our perception of reality, while the uncertainty principle adds a layer of unpredictability to the quantum landscape. Understanding this it's crucial as we embark on our quantum journey, setting the stage for quantum phenomenon awaiting exploration. Coming to our exploration of the quantum world takes us deeper into the mysteries of Heisenberg's uncertainty principle, a cornerstone of quantum mechanics that unravels the inherent limits of our knowledge in this. It's a fundamental truth shaping the fabric of quantum universe. The principle boldly states that the more precisely we knew the position of a particle, the less precisely we can know its momentum, and vice versa. And here's the kicker. It's not a flaw in our measurement tools, it's an essential property of the quantum world. You need to picture this a delicate balancing act on the quantum tightrope. The more we try to pin down a particle's location with precision, the more difficult to find its momentum, and vice versa. This trade off isn't it a merely inconvenience, it reflects to profound relationship of quantum properties. The uncertainty principle challenges our classical intuition, highlighting the dynamic and unpredictable nature of particles at the quantum level. It transforms our understanding of the quantum world, emphasizing the dynamic and inherently unpredictable nature of particles. This principle is the gateway to comprehending the details of quantum phenomena and sets the stage for the revolutionary concepts. Quantum states and the enhancing phenomenon of superposition. In the quantum realm, information isn't confined to binary choices of 0 or 1. Quantum bits or qubits exist in diverse array of quantum states. Imagine these states as the colors on an artist's palette, allowing particles to embody a spectrum of possibilities. Understanding quantum states is like understanding the unique language of quantum information storage. Let's bring this to life with a playful analogy. Imagine quantum states as Lego pieces. Each Lego piece embodies a distinct quantum state, and as they come together, they create a mosaic of quantum information. This analogy not only simplifies the complexity of quantum states but also emphasizes the modular and interconnected nature of quantum information. Now let's dive into the true circuitry of quantum mechanics. Superposition. It's the ability of particles to exist in multiple states simultaneously. You need to picture a quantum acrobat gracefully navigating between the classical extremes of 0 and 1, showcasing the magical nature of superposition. This inherent duality is not a limitation but a quantum blessing, exponentially expanding the computational capabilities of quantum systems. Continuing with our Lego analogy, envision these quantum Lego pieces suspended in mid-air, gracefully showcasing the various states they can embody. This playful representation captures the essence of superposition where particles dance between possibilities. Understanding quantum states, then superposition is like figuring the secret code of quantum computation. These concepts from the foundation upon which quantum algorithms are built. As we progress through this series, this understanding will empower us to unravel the mysterious quantum algorithms and their transformative potential. In this quantum world, measurement isn't a passive act of observation, it's an interactive engagement that reshapes the quantum state itself. When we measure a quantum property like position or momentum, it's not just about revealing the state, it's about actively participating in defining it. This dynamic relationship challenges our classical gut feeling, emphasizing the observer and the observed are entangled in a cosmic dance. The act of measurement is like a partner leading, shaping the steps of quantum state. It's a dance where observation isn't just witnessing, it's actively participating in the creation of reality. The quantum state is like a delicate canvas, and the act of measurement is the artist's brushstroke. When we measure a quantum property, the system undergoes a profound transformation. It chooses from its myriad possible states, and this choice is not deterministic but probabilistic. Reflecting the inherent uncertainty of quantum systems, the act of measurement is not a mere revelation, it's a collaboration that shapes the destiny and quantum system. You need to imagine the quantum state as a canvas filled with countless probabilities and possibilities. The act of measurement adds brushstrokes, narrowing down the possibilities and creating a unique masterpiece. This transformation is not predestined but unfolds probabilistically, introducing an element of unpredictability. Quantum measurement introduces a level of interactivity that distinguishes it from classical measurements. Understanding this dynamic process is fundamental to grasping the unique nature of quantum computation. As we progress through the series, quantum observer dilemma will become clear, paving the way for more advanced quantum concepts and applications. Quantum gates and operations. In classical computing, we are familiar with logical operations like AND, OR, and NOT, the building blocks of computation. Now imagine a quantum world where a whole new set of tools comes into play, quantum gates. These gates are the artisans of quantum computation, manipulating the quantum states of qubits in a ways classical operations could never dream of. Each quantum gate is like a unique instrument in an orchestra, contributing its distinct melody to symphony of quantum computation. Quantum gates, quantum gates aren't just fancy counterparts to classical gates, they are transformative operators that shape the quantum information stored in qubits. What makes them truly exceptional is their ability to operate on qubits in superposition. Imagine conducting an orchestra where each musician can play multiple notes simultaneously. That's the power of quantum gates. They enable us to process multiple possibilities concurrently, opening the door to unprecedented computational potential. You need to visualize this. Quantum gates as conductors guiding qubits in superposition, orchestrating a complex symphony of quantum information process. It's a dance of possibilities, and quantum gates are the choreographers. It's like akin to mastering the craft of quantum computation. They are the operators, the choreograph to interact the dance of qubits, enabling us to perform computational that were once considered instrumentable. Our journey began with a cosmic ballet where particles seamlessly transmit transitions between the classical definitions of waves and particles. This revelation shattered our classical certainties, inviting us to embrace the fluidity of the quantum world. Imagine particles dancing in a cosmic ballet, blurring the lines between waves and particles. We then delved into the delicate interplay between precision in knowing a particle's position and momentum. The uncertainty principle challenged the very foundation of uncertainty, navigating the nonce landscape of uncertainty. We realized that unpredictability is not a flaw but a fundamental characteristic of quantum tapestry. These quantum marvels are not mere theoretical abstractions, they are the guiding constellations lighting our way through the quantum revolution. Understanding these foundational principles is not just a prerequisite, it's a launchpad from which we'll soar into realms of quantum algorithms and applications. Please subscribe, like, share, and join our quantum community. Your active participation empowers the quantum journey for everyone. Please check one's fun assignment below in the description. Thank you.